Yeah, in this video we continue with decision analysis, and we are going to talk about probability-based decision making. In the first one we talked about perspective-based decision making, so now we're going to introduce probabilities. To remind you, the problem we're dealing with has three. We try to set up for Carnival, and we can either set up or don't set up. And if we set up, there are three possible states of nature on the day the carnival takes place. Rain, we lose 15,000. Clouds, we lose 5,000. Sun, we lose we make $10,000. And if we don't set up, we pay a penalty of $1,000. So we want to decide whether to set up or not. And also we have the three states of nature has probabilities 0.1, 0.3, and 0.6. Okay, so I'm gonna go to the probability-based decision making. In this case, we're gonna find out the expected value on average, how much we make if we pick decision 1 or decision 2. And so the payoffs for decision 1 are negative 15,000 if it's rain, negative 5,000 if it's cloud, and 10,000 if it's sun. And the corresponding probabilities are 10%, 30%, and 60%. So we multiply the probability by the corresponding payoffs, which what this formula tells us to do, and that gives me an expected value of $3,000. If we don't set up, the payoffs are going to be negative 1,000, negative 1,000, negative 1,000 with corresponding state of nature probabilities, and that gives me a payoff of expected payoff of negative 1,000. So we pick the maximum payoff, which is $3,000. So in this case, the optimal decision is to make decision D1, because on average, under similar circumstances, we make an average of $3,000 if we do decision 1, but we lose 1,000 if we pick decision 2. We call that the expected value of the optimal decision, or the maximum expected payoff, is $3,000. And you notice that this is the formula for expected value from your probability. That's the probability of state of nature. That's the payoff. And we do that for the three states of nature for each of the decisions 1 and 2. Okay. So we also can do expected regret criterion. So in this case, we pick the regret table, and if you recall, the regret table we regret 40. If we decide to set up, we regret $14,000 if it's rain, 4,000 if it's cloud, and nothing if it's sunny, because that's the correct decision. And in that case, we still have the corresponding probabilities 0.1, 0.3, and 0.6 for a expected regret of $2,600. If we don't set up, our regret would be 0 if it's rain. It's 11,000. It's also 0 if it's clouds, and 11,000 if it's sunny. These are the corresponding probabilities. We multiply them together and get 6,600. So the decision here is still D1, where the minimizing our expected regret, right? Now we're going to look at expected value of perfect information. Suppose in this situation we say, suppose we have the ability to predict nature perfectly. So we know if it's going to be rainy, we know it's going to be cloud, we know if it's going to be sunny. And so if we had this crystal ball where on the day we want to make the decision, we can tell what the state of nature is going to be exactly, then we make the right decision every time. And so in that case, that would be the value of our what would be the best we can do with perfect information. So we can look at expected value with perfect information. I'm going to call that expected value of D star. And so if you remember that if it was rainy, the best decision would be to not to set up, to cancel and lose $1,000, and that happens 10% of the time. If it was cloudy, the best thing is to not set up, again lose $1,000, and that happens with 30% of the time. And if it's sunny, we set up, and that would happen 60% of the time. So that's the best we can do. And in that case, we can make $5,600 even with the uncertain state of nature, but if we can predict it, if we had this crystal ball that we can predict the state of nature, what will happen on that day. So we call that the expected value without, this was expected value without perfect information, which is what we called that, we called that before just the expected value, and that's $3,000. So if we look at the difference, that would be the expected value of perfect information, which is $2,600. Remember, so the expected value of perfect information is the expected value without perfect information, and subtract from it the the expected value of perfect information is the expected value with perfect information, and subtract from it the expected value without perfect information. The surprising thing here is when we compute this, it turns out to be 2,600. So that's if we had a crystal ball, that's how much that crystal ball would be worth for us, because that's how much it adds to our expected value when we had just to make the decision based on the expected value criterion. But the surprising thing, it turns out to be exactly the same as the minimum expected regret. And is it surprising, really? So if we think about it, we realize that really it shouldn't be that surprising, since the gain in expected payoff from having perfect predictability, that should match the pain associated for not having that perfect information. So the two quantities turn out to be the same. Talk about risk analysis and sensitivity analysis. So risk analysis now helps the decision maker recognize the difference between the expected value of a decision alternative and the payoff that might actually occur. So the risk profile for a decision alternative shows the possible payoffs for the decision alternative along with their probabilities. For the decision to set up, which was our optimal decision, we said the payoff was 3,000, but actually when we set up, we're going to be either lose $15,000, lose $5,000, or make $10,000 with the corresponding probabilities. So 10% of the time we lose $15,000, 30% of the time we'll lose $5,000, and 60% of the time we'll make $10,000. So that's called a risk profile. Sensitivity analysis is sometimes a small change in the payoff or the probability will probably make us switch from one decision to the other. So it's the outcome, the best decision is sensitive to the values of the payoff or the probabilities, and sometimes we would like to analyze that. So the input can be probabilities of the states of nature or the values of the payoffs, and if a small change in one of these inputs causes change in the other ones, we can. So in a situation like this, if I were to change this, keeping this fixed, then this would change. Then I can compute the decisions based on different values of the probability, and I can basically graph that and to see when my decision switches. Okay. And this is the expected value criterion. Now I'm going to talk about Bayesian decision analysis for decision making under risk. Now we said the expected value is $3,000, we can make 2,600 more on average if we had a crystal ball. Typically we don't have a crystal ball, but we can have other alternatives, sometimes called additional sampling or getting extra information for a price. So let's consider one of these scenarios. Here we have the scenario where our carnival, where now there is an opportunity to purchase additional information, call it I, to assist in decision-making process. Suppose that a weather forecast can be purchased for a cost of $1,000 from a private forecasting service, and this forecast has been in existence for quite some time, and they give us their historical accuracy. This is how much accurate that forecast is, and we have an opportunity to pay that forecast if it helps us to improve our expected payoff. Now the question is, should we pay this forecast, and should we buy this forecast, and if we buy it, would it improve our payoff or would it pay for itself? Okay, so what does that mean here? These numbers here are given the state of nature is rain. This forecast has been accurate in predicting rain 70% of the time, incorrectly predicted cloud 20% and sun 10% of the time. Same thing here, when it was clouds, it predicted rain 20%, correctly predicted cloud 60%, and predicted sun 20%. Same thing here, when it was sunny, predicted sunny 70% of the time, and these are the other two probabilities for clouds and rain. But in our, so this one given the state of nature, we can tell if it's going to be rain, cloud, or sun, but that's not really what we want. What we want is the probabilities of the state of nature given the forecast. So we are here talking about conditional probabilities, and so we have to refer to Bayes' rule. So in this case, you have to go back and review Bayes' rule to be able to follow this and understand it fully. So the entries of the table are conditional probabilities of this form: P of I given Ik given S equal Sj. But we cannot, in order to be able to use them, we need the probabilities to be of the form S given I, not I given S. Okay. So we'll need to use Bayes' rule, and I will assume for a minute that we know how to use it, and we'll compute the revised probabilities or posterior probabilities, and then I'll give you later show you how to calculate those in a setup that would be useful for Excel worksheet. So these are called prior probabilities, and we want the posterior probabilities. Once we calculate the posterior probabilities, which are calculated here in this table, so here these are the probability of S given Ik, which means given rain, I have a row of probabilities here for rain, sun, and cloud. Given the forecast is cloud, this is actually I have rain, cloud, and sun, and the same thing given the forecast called for sun. These are my probabilities for actual rain, cloud, and sun. Okay, and so the procedure for computing the expected payoff with this additional or sampling information is this. First, we calculate the expected value without sampling information, and this is what we did before, so that's $3,000. Then we use Bayes' rule. This is Bayes' rule. We'll explain more about this, but please review that. And then this will give us these posterior probabilities, and then we're going to use the same payoff function. We are not going to include in this case the cost of additional information. So this is my payoff table now, and if the forecast calls for rain, I'm going to use this set of probabilities to calculate my expected payoff. If the forecast calls for cloud, I want to use this set of probabilities to calculate my expected payoff. And if the forecast calls for sun, I want to use this set of probabilities to compute my expected payoffs. So doing so, so for I1, if the forecast calls for I1, my expected value of D1, it's 0.368, see that probability, times the payoff, the posterior probability of rain, of cloud, times the corresponding payoff, the posterior probability of sun times the corresponding payoff, and I get negative 3,947. Expected value of D2, same probabilities, but the payoff here is the negative 1,000, which gives me negative 1,000. If the forecast is cloud, same thing. Now I use the second row for posterior probabilities, but the same payoffs. That gives me 0 here, and for the second decision gives me negative 1,000. And if the forecast goes for sun, I use the third row now of these posterior probabilities for rain, cloud, and sun, and I have my payoffs here. So that gives me 7,653 of expected payoff, and this gives me still negative 1,000. So to summarize, if the forecast calls for rain, I'm better off not set up. If the forecast calls for cloud, I'm better off not set up. If the forecast calls for sun, I'm better off to set up with expected payoff of 7,653. So my decision depends on what the forecast says, right? And that's what I have here. So then I would like to get my overall expected value, but to do that I need to be able to compute the probability of the forecast calls for rain, for cloud, and for sun. So if I get those probabilities, I can multiply them by these payoffs and get my overall expected value with sample information. So that's what I want, the expected value with sample information, and to do that I want to get the probability of I1, I2, I3, and this happens to be really the probabilities, and if you do these calculations, the probabilities in, where is that formula, the probability here in the denominator. So these probabilities already been calculated, and I'll show you that later. So P of IK would be given by this formula, and it will give me P of I1 0.19, P of I2 0.32, and P of I3 equal 0.49. So I take these probabilities, 0.9, 0.19, 0.32, 0.49, 0.19, 0.32, 0.49, and multiply them by the corresponding payoffs for rain, cloud, and sun, and that gives me $3,560. Okay, so that means I made more now with this additional information than without it. So the additional information was worthwhile, but was it worth paying $1,000 for it? So the expected value, what's the value of the sample information? And that's the expected value of the sample information is the expected value without the sample information minus the expected value without the sample information. So with and without, and that gives me $560. So that sample information is worth $560. How much did I gain? My expected gain is expected net gain, expected value with sample information minus the expected value without the sample information. But now I have to subtract my sampling cost. So really my sampling cost is way more than the value of my sample information. So I end up losing $440. And in other words, the cost of the sample information of $1,000 exceeds the value of the sample information, which is 560 by $440. How efficient the sample information? Our hope was that this sample information could get us a significant portion of what the crystal ball would get us, which is 2600, but it only got us 560. So that's called the efficiency of the sample information multiplied by 100, and that's 21.5% efficiency, right? And the next video would be on talk about a little bit about decision trees and the use of how to compute posterior probabilities. Thank you.